time. It's really nice to be with you all. I have to say, I'm just loving this conference so far. It's like all my heroes in one place. I've just learned a lot from so many people that have been making presentations and just the fantastic work you've done to make this SNAP community. So really deeply appreciate that, and also the people that built the BJC community, which we'll be talking about. So the title of our talk is Teaching with the BJC with NetsBlox, and I'm gonna just bring up some slides here. Let's see if I can get that to work. All right, I'm gonna have to share my screen, I think, right? Let's see, share screen, desktop, share, okay. Can you all see the presentation now? Yeah, okay, good. All right, so let's just begin by introducing ourselves. I'm Cliff Anderson, and this is a course that we'll talk a bit about how it came about, but just want to say that we started this in 2018, and we taught it for 4 semesters. We had a lot of help along the way with various folks at Vanderbilt that have been working in the area of visual programming languages and working on NetsBlox in particular, which we'll also discuss more. And then Gayathri, who's here with me, and I'll just introduce her briefly. She taught the last iteration of the course. Gayathri and I have kind of different backgrounds than most computer science educators. I mean, if I can generalize, in the sense that we don't have a degree in computer science. My background is in librarianship and digital humanities. And so over the past decade, I've just been working with, this group of people that called digital humanists. They're people from humanities backgrounds, but are trying to learn to use computational methods in their teaching and research. And out of that experience of teaching programming to non-programmers, I was invited by various people in the School of Engineering to try to turn this into a formal course for people that were coming from similar backgrounds and wanted to have a computer science course. Gayathri's background is in psychology and digital learning. She's taught in statistics and research methods, and also organized a workshop in data visualization. She's got programming background in Python and R, and so she wanted to take that experience of working with data viz and thinking about how to do statistical programming and also put it to the end of teaching a first level computer science course. So the course was approved in spring of 2018, and the description read, and when I first read this, it's like, oh my gosh, how am I going to possibly do this? Fundamental concepts of computing will be taught, including abstraction, algorithms, design, and distributed computation, with a hands-on curriculum focusing on translating ideas into working programs and developing a mastery of practical computational literacy. So in practical terms, we had 7 2-week units that we promised to teach everything from, quote, control constructs, variables, and functions to recursions, efficiency, and the limits of computability, with a good measure of networking and distributed computing as well, and a whole bunch of other topics. So we're trying to cover a lot. And the BJC became like the vehicle for us to try to think about this course. So one of our faculty members reached out and talked with folks like Dan Garcia and said, we'd like to use some of the material that you developed in the BJC. And they said, that's great. Happy for you to use the term BJC, but it was also in a sense like kind of reimagining of the BJC for our context. So we wanted to keep the goals of our offering consistent with the original intentions of the BJC. So here we go. And by the way, everything that I'm talking about is on a GitHub repository. So our syllabus and all the examples are available if you want to look that up. At the beginning of the BJC, as many of you know, and this is something that Dan Garcia said in a 2012 keynote address, the purpose of this course is to attract non-traditional computing students, especially women and minorities, but also English majors, to the breadth and depth of ideas in modern computer science. And this was just reiterated in 2020 in another paper about the design principles of the BJC, in which the author said, our absolute top-level goal is broaden participation in computer science. So like so many other places, we sensed at Vanderbilt that there was a gap in our course offerings for people that wanted to study computer science, but didn't want to commit to the major sequence, which would have them learning Java over the course of 1, 2, or 3 semesters. And we wanted to make it, we also wanted to encourage people to think about majoring in computer science or doing a double major, but who hadn't had the background and might not be able to immediately jump into a course like that because they hadn't studied in high school. So we wanted to level the playing field as much as possible for people coming into computer science. We also, and I think this is another sort of consonance with the BJC, we wanted to introduce sophisticated ideas for computer science while taking advantages of the affordances of visual computing languages. And this is something that Brian Harvey and Jens Monig explained way back in 2010 when they were developing this course at Berkeley. They said, Berkeley's approach to introductory computer science has been profoundly shaped by the seminal text that many of us know, the structure and interpretation of computer programs. And in our new course, we wanted to preserve the big ideas we gleaned from the curriculum, including recursion and higher order procedures as organizing tools for flow of control. And we had the same idea. We wanted to place a major emphasis on particularly functional programming language concepts, encouraging the use of idempotent functions and discouraging public variables, sort of trying to develop really what we thought were scalable and good programming practices while teaching, while also teaching things that students would run into in Java, like for loops and while loops. But still putting the emphasis on constructs like map, filter, reduce whenever possible. And our course was really taught through the lenses of learning to program, you know, another BJC notion that you develop good expertise in programming by actually reading, analyzing, and writing your own computer programs and then refactoring them. So we felt like, again, that was something that we learned from the way that the course had been structured in Berkeley. In our first week, we asked students to watch Dan Garcia's presentation of the BJC. It's a great TEDx talk he gave. And one of the things that's nice there is, you know, he programs V in the background. If you haven't seen it, it's sort of this way of introducing recursion with sort of random trees that grow. And then, of course, by the end of the semester, what was great is students were writing that program themselves. They learned enough to come around and be able to write that V program. And we even got them writing their own blocks, you know, so they learned how to write a repeat block by using that C-type structure and using higher order functions to implement it themselves. So what's really wonderful is they started with a set of blocks that, you know, that seem like black boxes, but by the end, they can actually know enough to build the blocks themselves. So they, you know, really deepen their knowledge, I think, of what was going on even with these primitives. Another challenge that we faced was, in the Vanderbilt context, was trying to like narrow down the scope in a way that we could effectively teach. Because as Brian Harvey mentions in a paper, Berkeley, and I don't suppose this is true, I think he's on the line with us now, so you tell me if I'm wrong. But you know, like Berkeley has a 14-week semester, and they met for 7 hours a week, 2 lecture hours, 4 lab hours, 1 discussion hour. By contrast, our course met twice a week for 75 minutes with no labs or precepts. And that's quite a big difference and kind of a problem, really. So we had to divide our classes into 2 parts, lecturing, you know, for about 30 minutes on social issues for each class, and then the rest of the time was programming exercises. But again, we didn't want to overwhelm students. We had to be able to teach these concepts in those sort of roughly twice a week, 50-minute blocks. Okay. And another difference is the use of NetsBlox. So NetsBlox is, as some of you may have heard in prior presentations, it's a Vanderbilt sort of development on top of Snap. And it adds several features to Snap that help us to understand network programming and distributed programming a little bit better. So first, it introduces a new primitive for message passing. And as Brian Brohl explains, messages are really similar to events that are already in Snap, but it's a message is an event that contains a data payload, which is great because then you can send messages with data to sprites in a project, but you can also send it across projects using a unique public role identifier that functions like something like an email address. Second, NetsBlox adds call and run blocks for making remote procedure calls. So we can call out to third-party services. They're really well encapsulated in these blocks, and then students can program with those data sources in their program, which I think made the program feel a lot more sort of real and lively to them. And finally, there's this idea of a room in NetsBlox. This allows students to build sort of network topologies and bring projects together that have different ways of communicating through message passing so that we can build things like client-server applications. And that's one of the things that we did in the course. So we drew in these features throughout the course, introducing remote procedure calls by the 4th week while we were teaching about lists, which is sort of the prerequisite for working with the data that comes back from those calls. And right after the midterm, we started working with message passing and building collaborative whiteboards and moving on to a client-server chat application. My favorite exercise is one that I have to give credit to Akos and Brian for developing, but it's illustrating a person in the middle attack, where we had students build a chat server, and then in the, they would build clients, I would build a server. In my server, I would put, they would be encrypting their messages, and then in my server, I would put something that would be looking for patterns. As soon as it discovered the pattern, it would decrypt the messages, silently change them, and then re-encrypt them, and then send them on so that you know, students suddenly discovered what a server can do if encryption doesn't work well. Lots of sophisticated ideas that NetsBlox allowed us to develop that are sort of add-ons to typical BJC. With that, I'm going to turn over to Gayathri, and she's going to talk about assessments.
Hi, can you all hear me?
Whoops.
Okay, I'm going to turn my video off because there's a lot of rain going on here and my connection is unstable. So I'm going to do that. It might make it better and more smooth through the presentation. So our version of the course had 4 major assignments. And the first was a set of 5 problems of increasing difficulty. Starting during the 2nd week, we assigned a so-called Parsons problem every week. For those who are not acquainted with this concept, Dale Parsons and Patricia Hayden introduced the idea of creating programming puzzles for students to solve. Rather than asking them to write programs from whole cloth, these were more challenging, but at the same time more interesting for them to complete too. So Parsons problems seek to make these more engaging, limiting the possibilities of limiting the range of possibilities and errors. An apt comparison would be to chess problems, which set up pieces on the chessboard to help learners recognize and solve certain kinds of tactical problems. Our problems were similar to that. We adapted some of the BJC exercises into Parsons problems while introducing a couple of our own devising. So creating a maze, for instance, or cloning, those were all some of the examples we used. The second kind of assignment that we had was a midterm examination covering the fundamental concepts we taught during the course, from assigning variables to processing lists with higher order functions. The third was a short paper focusing on a social, historical, or political topic related to computing. And then finally, we also asked students to develop and present a creative project of their own devising by the end of the semester, so they can use all these concepts, plus other concepts that they can bring to the table at that time too. I'm going to continue with readings. We departed from the standard BJC approach with our assigned readings. So the primary textbook in the BJC is Ken Leedon, Harry R. Lewis, and Hal Abelson's Blown to Bits, Your Life, Liberty, and Happiness After the Digital Explosion. Now the chapters provide coverage of legal and social topics ranging from copyright law to cryptology. As Brian Harvey noted in 2012, Blown to Bits presents some of the social issues of the internet era in a style that manages to be both accessible to lay readers and deeply informed by specific technical issues. Now, Blown to Bits has aged well for a technical book. Its coverage of the Communication Decency Act of 1996 remains stubbornly relevant as we continue to debate the merits of its safe harbor provisions for free speech in the age of Facebook and Twitter. Still, the undergraduates taking our course were in primary school when the book first came out, and making its discussions dated from their perspective. So, and the text lacks coverage of topics like algorithmic bias and filter bubbles, which have become major topics of conversation today. So a second edition is forthcoming, but the date keeps slipping. So we started with 2 other volumes. The first was Martin Erwig's delightful Once Upon an Algorithm, How Stories Explain Computing. As faculty with PhDs in disciplines other than computer science, we wanted to strengthen our presentation of computer science concepts with a strong introductory textbook. Of course, while evaluating potential textbooks, we ran smack into the problem that most teach computer science via some programming language or another. Eckhart Modro's Computer Science with Snap is unique in its teaching computer science with reference to Snap, but was a bit too advanced for our students reading the book. Proved challenging to us. So Erwig approaches computer science conceptually, discussing difficult topics like types, recursion, and the limits of computing by reference to books and films like Sherlock Holmes, Harry Potter, Back to the Future, and Indiana Jones, very much in the age that our students were, at least familiar with most of these movies. It's sad to say that when I was talking to them, a lot of them haven't seen any of the Indiana Jones movies or Back to the Future movies, but they're very familiar with Harry Potter. So that was very helpful. Our second assigned reading was Claire Evans's Broadband, The Untold Story of the Women Who Made the Internet. By the way, this was my favorite book. It talks a lot about the women who shaped computer science and who are pretty much forgotten in a lot of time during the initial years. In each chapter of Broadband, Evans presents a vignette or two about the women who made significant contributions to computer science. And given her emphasis on the development of networking and communication protocols, Evans's book provided support for our discussions of distributed computing. But her vignettes also helped us to broaden students' perceptions of innovators in computer science, highlighting key people like Ada Lovelace and Grace Hopper to contemporary scientists like Wendy Hall. We also assigned primary source readings like the classic Alan Turing's Computing, Machinery, and Intelligence paper during our treatment of AI. Turing's paper introduces the imitation game as a way of evaluating whether a machine had learned to think. Some of my students had watched the movie, by the way, and were able to supplement the concepts from the paper with what they had learned in the movie. So that was good. Turing also discusses 9 potential objections to the notion of thinking machines. As a recent discussion on the 6E mailing list brought to light, Turing also introduced uniformed opinions, for example, about Islamic theology into his paper. To give students a contemporary perspective on the topic, we paired the reading from Turing with a video by Stephanie Dinkins, media artist and associate professor in the Department of Art at Stony Brook University. In her video, Dinkins interacts with Bina 48, a humanoid robot, on topics range from racism to robotic rights. Our emphasis on course readings perhaps inadvertently gave away our disciplinary origins. As Amy Coe, professor at the University of Washington, the iSchool at the University of Washington, wrote on Medium, as a computer science major, I regularly received explicit signals from CS faculty that not only were books irrelevant, but they were to be explicitly devalued. But we were using these books as a humanist, librarian, and social scientist. These books are our stock in trade. But the get ready to read flares that we saw from students probably meant the quantity of the reading required surprised them. Then moving on to our final projects, we dedicated the second half of the semester to the final project. And this year it worked out really well because I taught most of my initial classes before spring break, and after spring break, we all moved to online. So it really helped that there was like a clear break from the way we taught the first part to the next part. After the midterm, we lectured on topics from recursion to the P versus NP problem, but we did not test the students on those topics, wishing to avoid anxiety about these traditionally difficult subjects. Students devoted themselves instead to final projects that they presented to one another during the final week of the semester. The range of projects varied widely from simple games like Snake.io clones to literary and scientific programs. One of my students had created a Jeopardy version, and another person had done a Monopoly, so they had used other games like that too. A few students worked on computational poetry generators. An ambitious student implemented and visualized a single linkage clustering algorithm that she had learned in her biology course. A significant number of projects drew on data from NetsBlox RPCs. If students wish to work in pairs, we required them to make use of NetsBlox message passing features. Students who took the STEAM option developed 2-player soccer games and also a peer-to-peer Venmo-like application. One pair of students in my group, one of them was in Korea and the other person was in Michigan. I mean, it was really interesting to see how they collaborated across these time zones and distance, and they created a tennis game that could be played between 2 players, which was very interesting. And finally, the course never took off in the way that we anticipated at Vanderbilt. We offered the course over 4 consecutive semesters, and enrollment averaged fewer than 20 students per offering. The most significant problem was the institutional context. The School of Engineering offered the course, but the majority of students came from other schools at Vanderbilt, primarily the College of Arts and Science, but also Peabody College of Education and the Blair School of Music. From our initial survey of students' goals for the course, these students recognized the significance of computer science for the future, but most had not had the opportunity to study it at even at the high school level. So a lot of them were new to coding. The sequence of courses for majors and minors in computer science would represent too great a commitment and possibly prove overwhelming. But the beauty and joy of computing was too elementary for students enrolled at the School of Engineering. And the problem was that our course did not fulfill the graduation requirements required for students at the College of Arts and Science, which meant that they took it as a pure elective. So for better or worse, many of the students who took the course, they are probably going on to do some other courses in coding, but also they wanted to be to be there because there was no extrinsic reason for enrolling beyond interest in the topic. Turning it over to Cliff right now for future directions.
Okay, thanks, Gayathri. Can you still hear me?
Yes.
Okay, great. Just to wrap up a little bit about future directions. So, as Gayathri said, this is a course, unfortunately, that we won't be repeating, at least in the short term. But we are thinking with the Computational Thinking and Learning Initiative, which is a Vanderbilt institutionally funded interdisciplinary group of faculty and staff that are seeking to expand computer science across the curriculum, about how to maybe offer courses like this in a different way. So the CTLI, for shorthand, gathers folks from computer science, education, information scientists, and humanities to think about computation in all disciplines. So I'm hopeful that a new version of this course will emerge, but perhaps with more of a focus on particular disciplines. We do have to sort of think about this question: what does it mean to teach programming in disciplines other than computer science? And I'm sure this is already happening at your institution, certainly happening at Vanderbilt, but not in systematic ways. For example, I've taught a course in the past with a colleague from the Divinity School on textual analysis with X-query programming language. I've also worked with a professor of musicology who works with a kind of data format called MEI. She and I offered a course on the history of Berlin, which is, she also has a specialty in German studies, where we did a lot of digital mapping and learned how to use data structures like JSON and databases like CouchDB. I know that there are other colleagues that are teaching in humanities or in media arts with P5.js and with C# to create 3D games in Unity, but there's no structure, at least at Vanderbilt, for helping students to navigate those courses or pull them together in any kind of systematic way. And finally, one thing that I've really learned a lot from is seeing how the P5.js community works and how the people are teaching programming to new media artists. And this, I think, this focus on thinking about how artists learn to program harkens back to a comment that Eric Roberts made during a SIGC discussion about the BJC in 2009, in which he said, if we want to produce software artists, it might be useful to experiment with alternative educational strategies similar to those used to prepare artists, writers, and musicians. And I've really thought about that, and I've wondered, in our course, we tried to balance examples from mathematics, science, and humanities, but maybe we didn't do a great job sort of trying to pull out the beauty that's latent in all those disciplines, because we kind of shortchanged each one of them. So how could we help students to use computer science to sort of bring out the beauty in their own disciplines in a deeper way? I think this would require, reshaping this course again with a focus on those particular disciplines. And we've been trying to do this, as some of you may have attended our text mining discussion in the last half-hour slot. We're trying to focus now particularly on text mining, but using NetsBlox and using the BJC principles. And I think we're going to continue to experiment in that way. But for now, let me just thank you again for listening to our talk, and we'd be happy to answer any questions. And I'm going to stop sharing here. Hopefully there are some questions. Well, Gayathri, do you have any final words before we close up?
It was great working with you, Cliff. Thank you.
Likewise. Oh, do you have a new name for your course if you're revamping it? You know, I don't know if it might be like the beauty and joy of computing in the humanities. Can we just like extend the name to like reference the discipline? We haven't thought that far. We'll have to think about it.
There's a comment from Mark Schoenfeld. Do you think it's an issue that the different disciplines have such different ideas of beauty? You want to take a stab?
Yeah, I mean, I think that's kind of what I was trying to get at, Mark. I think that there, you know, there's obviously like a lot of examples in which you code like a kind of like a Mandelbrot set, which I think is in the background of at least one of Dan Garcia's backgrounds that he's using on Zoom. I mean, you know, things like that are inherently beautiful, but it's a different type of beauty than we might say that you discover in, you know, a novel. And so one of the things that I think we want to think about is how do we deal with the different aesthetics from these different disciplines? How do we think about computing beauty in different disciplines?
There's another question. Are you doing anything with visual arts in addition to music and text?
Not so I realized as I was teaching this, and Gayathri, I'd be interested in your thoughts about this. I realized it's really quite hard to come up with examples that draw on sort of all these different modalities at once. And so like thinking about a computation that works on a text, but also does something visually interesting on the stage turned out to be a real challenge for me. I don't know how you experience that, but I think it shows that the crafts, you know, crafting the educational side of this, working on the pedagogy. I totally now understand why so many people spent so many hours on designing the BJC examples, because it's not easy to get all those things firing at once.
So the only things that come to mind are some of the things that we did in class related to visual arts, maybe creating fractals, for example. We used, you know, I was showing them the BJC version of that, and they were experimenting with creating fractals, and some of them came up with like really unique and very complicated figures, and they were able to do that just from, you know, using the program's different steps. But also we did the call function to call pictures like museum paintings in the museum and so on, and some of them were getting into that. To actually look at the paintings and then talk about it. We talked a little bit about how one of the more, I think it was Rubens' paintings, was recreated by AI. We talked a little bit about how that was, you know, possible now and what AI is able to do, but not anything linking directly into the programming itself.
I was muted. Anyway, thank you all for listening. That's all I have to say, and appreciate you all being with us.
Thank you all. Thank you all for listening to our talk.